All right, so nobody solved this one on the homework, and I don't blame y'all because this problem is very not nice, but it's still doable as long as you're organized about it. Okay, so the game of connects contains one 4-unit piece, two identical 3-unit pieces, three identical 2-unit pieces, and four identical 1-unit pieces. How many different arrangements of pieces will make a 10-unit segment? And the rest is just an example. The 10-unit segments consisting of the pieces 4, 3, 2, 1 and 1, 2, 3, 4 are such arrangements to include. And so now we have to do casework on the specific set of pieces that we have because we care about the order of the pieces. And so our first part that we're going to do is we're going to consider how many ways we can build a connects when we have the 4-piece used. So for example, if we use the 4-piece, and then we're going to try and do them kind of like alphabetically, but basically try and use as large pieces as possible. So one way to do this would be to have one 4-unit pieces and two 3-unit pieces. And this can be arranged in 3 ways. One 3-unit, one 2-unit, and one 1-unit. Basically, we're breaking this 3-unit down, and this thing has 4 factorial or 24 different ways to do that. Next, if we can break this 2 further down, and this has 5 times 4 equals 20 different ways to arrange it. Then we have 4, 2, 2, 2. We're breaking this down even further. Actually, we're assuming that now, basically this is 1, 3. We're using 2 3s here. We're using 1 3 for these. And now we're using no 3s for the followings. And so there's 4, 2, 2, 2. There's 4, 2, 2, 1, 1. And then 4, 2, 1, 1, 1, 1. And so the number of ways is this one has 4. You just choose the position of the 4. For this one, it'll be 5 to choose this position of 4 times 4 choose 2, which is 4 times 6, which equals 30. For 4, 2, 1, 1, 1, 1, you first choose the position of 4, then you choose the position of 2, and then the ones are determined. So there's, once again, this is actually a coincidence, 30 different ways to arrange it. And we can't break it down any further because we only have 4 pieces of length 1. The set of value things we have to build are these. This is what we have to build it. And so that's part 1. That's the number of ways to do it if we have the 4-piece. And just as like a quick substep, the sum of these is 27, 47, 51. There's 111 so far, 111 ways if we have the 4. And now we consider what happens if we don't have any 4s and our largest piece is a 3. So if we're using 3s, then there's 3, 3, 2, 2, because we only have 3 3s. That's the maximum number of 3s we can use. So the number of ways we can do it when we have 2 3s is we have to have something like this. 2 3s. When we have 2 3s, these are the 3 possible ways to get to 10. And this has 4 choose 2 equals 6 ways. This can be done in 5 times 4 choose 2, which is 30 ways. And this one can be done in 6 choose 2, which equals 15 different ways. And then next, this is so long. If we have 1 3, then there would have to be of the form 3 2 2 2 1, or like 3 2 2 1 1 1. And this has 6 times 5 equals 30 different ways because we fixed the 3 and the 1. For this one, we have 6 times 5 choose 2, which is 60 different ways to build out our connects. And then our final case is what happens if we don't even have any 3s and our largest one is a 2. And the only way to do that is with 3 2s and 4 1s. And it says 7 choose 3, which equals 35 different ways to build that out. And so you take the sum, this is 36, 51, 81, 141. And then so the total number of ways is 111 plus 141 plus 35, which is 287. That's not right. Let me go back and check. Okay, 6 plus 30 plus 15 plus, this is meant to be a 20. Yeah, okay, this is meant to be a 20. I miscounted. Okay. So here we actually have 5 different blocks and we're trying to arrange them. And so we have 5 ways to place the 3 and 4 ways to place the 1. So there's actually a total of 20, and this is 131. And so you have a total of 277 arrangements. This is a horrible problem. Although I suppose it was useful back in the day for like stopping perfect scores.